this video, I'd like to explain the existence and uniqueness of a differential equation in differential form. I forgot to add the word exact, so we look at the exact differential equation in differential form and show the existence and uniqueness. Recall in our class that the condition that guarantees that this differential equation is exact as an exactness theorem. By the definition of this differential equation being exact, there is this two variable function f of xy. There's a two variable function with its two independent variable, its derivative with respect to x is exactly the coefficient in front of dx. Partial with respect to y is exactly coefficient in front of dy. If there is such a two variable function, we call this equation exact. So that's the definition. But by the theorem we call the exactness theorem, if we have this condition, the partial derivative of this one with respect to y and partial derivative of this one with respect to x, if they're equal to each other locally, not globally, locally this guarantees that these two variable functions are realized at a partials of this function. And we have this initial condition. As you can see, I wrote this initial condition more generally as the initial condition of function xt and yt, and they're hitting a and b. Often this one is viewed as the function y of x such that y of a is b, but this is more general. It makes more sense in this context. So by exactness theorem, because this one is satisfied, we know the existence of this two variable function around this point a comma b, because the parameterization will go through this a comma b such that this function has this partial derivative. So these are just a collection of some results that we put together. Let me erase this one. So from here is an argument that goes to the argument of the uniqueness. So here I copy the differential equations again. This equation itself does not include the condition, the partial of this with respect to y, that with respect to x being the same. That part is not part of the condition. I mean part of the differential equation. That's the extra condition that's given. So suppose they're all parameterization x and y such that this differential equation of x prime t and y prime t here, this is satisfied. So we assume there is this function xt and yt, which is rewritten here. Now by the exactness, the property the property of this m partial y and partial x, that they being the same, by the exactness theorem, this is realized as the partials of a two variable function like this. So this one is replaced by partial with respect to x of a two variable function, partial y of the same two variable function. So here we use the exactness theorem. So this is the fun part. If you look at this equation, not just the dx and dy, but with the dt, if you write it here, if you have taken Calc 3, this is exactly how the chain rule works. And in my course of differential equation, I also introduced why this chain rule works like this. So if there's ever a two variable function like this, and if x and y are parameterized by one variable t, the way this f of xy is differentiated is exactly like this. So this is, the left hand side is the derivative of this two variable function composed with one variable. So going from here to here is not integral or anything. It's just simply the chain rule. If you differentiate this one, left hand side is that one. That's the identity. So again, going from here to there, there's no integral. It's simply by the chain rule. Identically, this left hand side is equal to this left hand side in here. So reversibility is easily established in here. In the next part, we do the integral. So left hand side is whatever this complicated part is just a function of t, but it is written in terms of x, a function of t, y, a function of t. So we're hitting this one with the one variable integral with respect to t. So t is going to be our main variable, So instead of t, I'm using uc here and integrating with respect to u. Right hand side is simply this one with the du. Because it's constant, this part will be 0. So this is interesting part. If you look at it here, inside with this dummy variable u and xy before independent variable now is dependent variable of u, this whole thing is differentiated and integrated, right? So this operator, differentiated and integrated, that obviously cancels here. Or you can look at this entire thing, this part here, as an antiderivative of the entire of this part. So by theorem, you can just have this antiderivative right here. That antiderivative of this entire function is of course inside it here, so that's the antiderivative. So there's a theorem that this is always the values of difference of the values of any antiderivative, and that's the theorem. So we have this strong implication right here. So that value evaluated at t, evaluated at c. Right hand side, because it's a constant, if you evaluate and subtract, you will end up at 0. Because it's not indefinite interval, it's a definite interval right hand side. Well, if you plug in t, that's xt and yt, those are the arbitrary value. C is the initial value a and b. So left hand side becomes this two variable Cartesian equation where there's no derivative, and this is just a constant and equal to 0. So that shows the uniqueness of the Cartesian equation. So from here, if there's ever a differential equation like this, and which happen to be exact with that initial condition, it must be this Cartesian equation. So if you look at this reversibility of this argument, it's pretty simple actually. All the argument is reversible. So the only candidate we have here is by the reversibility understood at each step that is actually satisfying this condition. So if you differentiate this one, you can easily obtain that. So from there, we can prove the existence as well. Thanks.